Okay. So hello everyone. We'll start with the first live session for this course on hydraulic engineering, which is being taken by Professor Mohammad Saud Afzal from IIT Kharagpur, the Department of Civil Engineering. Uh, Before we begin with today's session, let me share my screen and please let me know whether my screen is visible or not. Yeah. Is it visible, my screen? Okay, fine. Okay. So, welcome to this live session, the first live session for this course on hydraulic engineering. Now, I hope that you have already gone through the contents of at least of week 1. You have gone through the lectures already. So, it is a very fundamental course which is fundamental to various aspects of civil engineering, not only in civil engineering but also this particular subject of hydraulic engineering. If you look at the fundamentals, it is basically fluid mechanics. So, it is equally relevant for mechanical engineering, chemical engineering, and other relevant branches. So, before we start with today's session, briefly about me. My name is Shubhrangshu Purkayastha and I am a research scholar in the Department of Civil Engineering at IIT Kharagpur, and I am working under the course instructor for this course, Professor Mohammad Saud Afzal. My current research is focused on bluff body flows and computational fluid dynamics. So, for the next 12 weeks at this particular time slot, I will be conducting the live session, that is from 4 to 6 p.m. Every Saturday, and these lectures along with this content will be made available to you from NPTEL. Now, first of all, the contents of this course. Now, if we look briefly, the contents of this course include the first part uh, is the basic fluid properties, where sorry are the basic fluid properties, where you will learn about the uh, where you will learn about the different aspect, what are the different fluid properties which are important to us, specifically from the point of view of engineering applications and engineering properties of the fluid. So the basic fluid properties, you must have gone through the lectures, you have seen that include density, mass density, then weight density, then surface tension, then viscosity. So all these are very important properties and which will be required till the end of this course and maybe other higher courses which builds on this fundamental course of hydraulic engineering. Just one second. Yeah. After that, we have hydrostatic pressure and its measurement. So what is the meaning of this term hydrostatic? The meaning of this term hydrostatic basically means that when the fluid is at rest. No. So the meaning of this term hydrostatic basically means when the fluid is at rest. So whenever the fluid is at rest, what are the different associated phenomena? What are the hydrostatic forces that the fluid incurs? All these things are covered in the second topic, which is the hydrostatics, or the fluid is at, when you say the fluid is at rest. Okay. Then we have hydrostatic forces on surfaces. So when a surface is submerged vertically in a liquid, when it is submerged horizontally, when it is submerged in a liquid making some angle, all these cases comes under hydrostatic forces on surfaces. Then we have pressure and its measurement. So what is actually fluid pressure? What is Pascal's law? How fluid pressure is measured using different types of manometers? All these things are discussed in uh, unit 2 and unit 3. Then one very important aspect is the aspect of buoyancy. Okay, so what are buoyant forces, what is center of buoyancy, how do you analyze the buoyant forces, all these things are discussed. Then we have fluid kinematics. Now this is important. whenever we are studying fluid mechanics, whenever we are studying fluid fluid mechanics, or for that matter any mechanics, okay, whenever we look at this word, sorry, mechanics, there are two aspects to this mechanics, okay. One is your statics, and the other part is your dynamics. So statics and dynamics, so as the name suggests, statics basically, so before in fact there is one broader one broader aspect. So when you have mechanics, mechanics is basically divided, means before the statics and dynamics there are two subdivisions of this mechanics. One is kinetics and then kinematics, okay. And this kinetics actually further subdivided into statics and then dynamics. So what is the meaning of these words? So mechanics, we study the force as well as the motion as well as the responsible forces. Now kinetics deals with the forces, that is, whenever you apply some force on a body, what is the resulting motion, and everything is considered in kinetics. However, kinematics deals with only the velocity and acceleration, that is the motion portion, not on the forces responsible for that motion, okay. And under kinetics means where you study the forces responsible, we have two types of domains basically. One is statics, means when the body is at rest, and the other one is dynamics, when the body is in motion. So if you look at this, then we have fluid kinematics. So in fluid kinematics, we study about the fluid velocity, then the acceleration field, okay, then the potential function, stream functions. All these things are considered in fluid kinematics, okay. But we do not consider the underlying forces. The underlying forces are studied. The underlying forces are studied in this particular chapter, which is the fluid dynamics, okay. So this kinematics is basically only motion aspects, okay, only motion. And here in fluid dynamics it is motion plus the forces, okay, plus the forces which are responsible for causing that motion, that is being studied in fluid dynamics. After that we have Reynolds transport theorem. Now Reynolds transport theorem is again a very important theorem. Why this is a very important theorem? Because Reynolds transport theorem is a very important theorem because here we uh, whenever you study fluid mechanics, there are there is a concept of system, and there is a concept of control volume. Now what is a system? A system is basically something, okay, it is basically whenever you are studying or analyzing a problem, a system is basically something whose mass is always conserved, okay. However, in control volume, the mass flows across the surfaces, the mass flux is there, okay. So Reynolds transport theorem, that is RTT, gives you a mathematical form how the system parameters are related to the control volume parameter. And in very simple words, all the conservation equations, that is the conservation of mass, linear momentum and angular momentum, can be derived from the Reynolds transport theorem with suitable not modifications exactly, with suitable whenever you put appropriate terms along the appropriate terms for the different conservation equations, you can derive everything. Then next we have laminar and turbulent flows, okay. So laminar flows and turbulent flows basically with respect to pipe is discussed in this course, okay. So for pipe flow, it is basically decided by the Reynolds number. So for pipe flow, the Reynolds number is given by rho v d by mu, where rho is the density, v is the velocity, the average velocity across the pipe cross section, d is the diameter of the pipe which is taken as a characteristic length, and mu is the coefficient of dynamic viscosity. So for laminar flow, this Reynolds number is less than 2000, but only in case of pipe flow. And for turbulent flow, this Reynolds number is greater than 4000. And in between 2000 and 4000, we call it that it is in transition. Then we have boundary layer theory. So what exactly is a boundary layer? You will get to know about all these things in details when you will go through the lectures. But just to give you a brief idea of what all is included in the course, boundary layer theory. A boundary layer forms when a fluid flows over a solid surface. Now, when the fluid flows over a solid surface, there is something known as no slip condition, which you must have come through if you have already gone through the lecture of week 1. Okay, so what is no slip? No slip is basically a condition which tells us that suppose this is a solid surface and a fluid flows past this solid surface, then on this surface, okay, the relative velocity, not the actual velocity, but the relative velocity, sorry, the relative velocity between the fluid particles and the solid surface becomes zero. So what does it means? That if the surface is stationary, if the solid surface is stationary, then the fluid particles which are in contact with this solid surface will have zero velocity. And if the surface is a moving surface, if the solid surface is a moving surface or it's a translating surface, then the fluid particles which are in contact with this solid surface, okay, the fluid particles which are in contact with this solid surface will have the velocity of this solid surface itself. So that's how you'll be getting a relative velocity of zero. Okay, so because of this no slip condition, okay, what happens? A velocity gradient develops, and the thickness, okay, the thickness along, say this is our y direction, the thickness along y direction till which this velocity gradient exists is the boundary layer. Okay, so the various analysis related to the boundary layer discussed in this unit, which is boundary layer theory, which is again very important if you consider practical applications like river engineering or ocean engineering or flow of wind across tall cylindrical structures. This boundary layer theory is very important. Then we have dimensional analysis. Now whenever we perform experiments related to fluid mechanics, or uh, say you want to study say you want to study the motion of the sediments, okay, which lie on a river bed, okay, and suppose you want to perform some experiments related to it, then whenever you are conducting experiments, it is very important that this dimensional analysis is done, because you cannot replicate the actual dimensions of a river. Suppose you consider river Ganga or river Brahmaputra, you cannot make uh, means you cannot replicate the actual river which is having a very large width and very large length in your lab. So in our lab we used scale models, but how much that scale should be, okay, so that your model that you have constructed in the lab actually replicates, okay, or it is giving you a good prediction for the actual field cases, okay, you need to have some scale values of the parameters. So how that scaling is done depends upon this particular topic, which is dimensional analysis. Okay, then we have free surface flow. What exactly is free surface flow? Free surface flow is also known as open channel flow, whenever a flow takes place where the free surface is subjected to a constant pressure, and in most of the cases it is atmospheric pressure, we call it free surface flow. For example, if you consider the flow in rivers or flow in oceans, these are examples of free surface flow. In case of pipe also, if the pipe, say there is a circular, sorry, say there is a circular sorry, yeah, so say there is a pipe, okay, say circular pipe, roughly circular pipe, and it is not flowing full, so what happens? This is the free surface, okay, and the pressure here is atmospheric pressure everywhere on this surface, okay, so this is also example of free surface flow. But if the pipe is flowing full, then it is not a free surface flow, then it is a classic example of pipe flow. After this, we have viscous fluid flow. Now, viscous fluid flow is a very fundamental chapter, because here you will be looking into the various deformations. Okay, the various deformations Now, how viscosity is important, what are the consequences of fluid viscosity, okay, all these things will be discussed in viscous fluid flow. Then the last two units, sorry, yeah, the last 2 units, computational techniques in fluid mechanics and fundamental water wave mechanics, might be two new chapters which are generally not included in our college curriculum for civil engineering courses, but for those who are from ocean engineering or naval architecture background, they might have some idea. Now, these computational techniques in fluid mechanics, basically nowadays we know that lots of software are available which are used for studying various fluid flow situations. Now, what they basically do, these softwares do, see, whenever we solve any problem on mechanics, okay, whenever we solve any problem on mechanics, what we try to do is we try to apply the conservation equations, okay, we try to apply the conservation equations. Now, what are these conservation equations? These conservation equations are conservation of mass, conservation of linear momentum, then we have conservation of angular momentum, and we have the conservation of energy, okay. Now, in case of fluid, the conservation of mass equation is known as the continuity equation, and the conservation of linear momentum, after suitable after you have applied suitable assumptions which are relevant to fluids, is the Navier-Stokes equation. So these continuity equation and Navier-Stokes equation basically forms a system of differential equation where you have four different unknowns, which are, if you consider incompressible flow case, which are u, v, w, that is the velocity field, and p, pressure. And we have four different equations. One is the continuity or mass conservation, and three equations are the Navier-Stokes equation. Because it is linear momentum, momentum is a vector quantity, so for each direction we have one. So Navier-Stokes equation along x-axis, along y-axis, and along z-axis. So these three equations plus one continuity equation gives us four equations. So four equations, and we have four unknowns, okay. However, exact mathematical solution to this system of equation is not available till date. In fact, whether a unique solution exists for this particular system of differential equation is still in question. So that's why whenever we study any complex fluid flow situation, whenever we study any complex fluid flow situation, we try to uh, obtain approximate solution. We try to obtain approximate solution to this equations, okay, by some suitable numerical method. So whenever we are using some numerical technique, we are not finding a solution which is exact, but we are finding an approximate solution. So this entire approach, okay, this entire approach is known as CFD or computational fluid dynamics, okay. Now you will see in this particular course only, if we simplify the Navier-Stokes equation under certain assumptions, then for example in pipe flow or maybe flow between two parallel plates, this Navier-Stokes equation becomes so simple that for those cases there is an exact solution. But if you consider the entire Navier-Stokes equation in general, in totality, then there is no exact solution available, and we go for computational techniques. Now there are different techniques available for the solutions, which include FDM, which is the finite difference method. Then we have finite volume method. Then we have FEM, which is the finite element method. Apart from this, there are many other methods like spectral element method. Then we have boundary element method. So there are different methods available. Then we have some meshless techniques available like smooth particle hydrodynamics. So there are different techniques, but these are all approximate. These all these techniques gives approximate solution to the Navier-Stokes equation. So a very basic introduction to this CFD techniques is provided in this unit, which is computational techniques in fluid mechanics. And the last one is fundamental of water wave mechanics. So water wave mechanics is relevant to ocean engineering. Now if you consider a ocean, now apart from the water current, okay, that is the flow, we also have water waves, and these water waves have uh, significant impact on the flow hydrodynamics associated with any ocean or coastal engineering structures or any ocean engineering phenomena. So it is very important, if you are studying hydraulic engineering, you should have a very good idea of water wave mechanics. So these last two units, since it is not generally uh, present in the curriculum for civil engineering, it is very important because application wise these two chapters are very important. Maybe in higher studies if you go, you'll find these subjects, but at UG level, uh, uh, if you look at the entire course curriculum, these two chapters it is very difficult to get in the curriculum of civil engineering. So these two, the last two units are the specialties or USP for this course. So this is the fundamental. Now, now with a brief introduction to the contents of this course which you'll be learning, and I would like to tell you that the live sessions will be based on the problems associated with each one of these units. Now what are the purpose of these live sessions? Now it is very important, there should not be any confusion. Okay, now the purpose behind these live sessions are to provide you with some additional contact hours for problem solving. Now, as you know that at the end of every week lecture, you need to solve some problems as a part of the assignment. And finally, if you appear for the certificate exams, there also need to solve the problems. So these live sessions are meant to give you some confidence where you will be solving some additional problems. Okay. Now, we'll during these live sessions, it is also intended to highlight the critical topics, okay, where you need to put some extra effort, not only for this particular NPTEL course, but also for some other competitive exams like GATE or engineering service exams. So, which topics need some uh, further effort, okay, and which topics are important, from which topics you can expect uh, questions, okay. So all these things will be discussed. So ultimately the aim is to develop the confidence, build the confidence in you for solving the assignment problems. You can also consider these sessions as doubt clearing sessions. Suppose in the live sessions, suppose in the lectures that you have gone through, you have some doubt, that also you can clear here, that is also fine. However, last time we have seen that many participants actually start asking doubts on the problems of the assignment, okay, the assignment for this particular uh, session that is running. But you need to keep this in your mind that the actual problems for this particular terms assignments will not be solved or entertained here. Okay, for that, for the assignment problems, if you have any doubt or any confusion, you please post your doubts or confusion in the forum. Okay, you post your queries there. In this particular live session, uh, we'll be solving some sample problems. We will be clearing your doubts related to the concepts, okay, or anything other than the assignment problems. Okay, other than that, post all your queries in the forum. So with this, we'll begin with the actual content. What is a fluid? That is the first question. Then, what is the difference between fluid mechanics and hydraulics? Now, if you have looked into the name of this particular course, it is known as hydraulic engineering. However, the contents are more or less the contents of fluid mechanics. So, what is the difference between fluid mechanics and hydraulics? But before coming to that, we should know what is a fluid. Okay, we should know what is a fluid. So, what is a fluid? To answer this question, we should begin from the states of matter. So the three states of matter from the engineering point of view are solids, liquids and gases. And the obvious differences that all of us know is that in solids the molecules are very closely packed. In the gases molecules are very widely spread, okay, and in between we have liquids, okay. Now out of these three states of matter, you must know all these things, that gases and liquids are considered as fluids. So the question is, why gases and liquids are termed under one term which is known as a fluid. So with this there comes the basic definition of a fluid. So what is the basic definition of a fluid? The basic definition of a fluid is that a fluid is a substance that deforms continuously. A fluid is a substance that deforms continuously under the action of a shear force, okay, however small the shear force may be, okay, however small the shear force may be, okay. So fluid is a substance that deforms continuously under the action of a shear force, however small the shear force may be, okay. So that is something which differentiates a fluid from a solid. And this particular property, okay, this particular property, that is deforms continuously under the action of a shear, okay, is exhibited both by gases and liquids, okay. So that's why these two are termed together as fluids, okay. Now if this is the case, then let us look at what is the basic idea behind Newton's laws of viscosity. Okay, what is the basic idea behind the Newton's laws of viscosity? You consider that there is a fluid block. Okay, you consider that there is a fluid block which is fixed at the bottom, and similarly there is a solid block which is fixed at the bottom. Now on the top surface you apply a force, you apply a shear force F of same magnitude, okay, of same magnitude for both. So this is our liquid, okay, this is our liquid, I'm writing L, sorry, not liquid, say fluid F, and this is our solid S. And on both everything is same, okay, dimensionally these blocks are same, okay, and you have applied a shear force of same magnitude on both this blocks, the fluid block and the solid block, okay. So what will happen? Shear deformation will occur, okay, or angular deformation will start to occur. Here also shear deformation will occur. But the difference, what is the difference between these two? Once you remove this shear force, in case of this solid, what will happen? It will come back to its original position, okay. There may be slight deformation, there may not be slight deformation. This will depend upon what? This will depend upon the elastic limit, okay. This will depend upon the elastic limit, but that is for this solid, okay. Means whenever you are providing the deformation, if it is within the elastic limit, then it will come back to its original position, it will regain its original position, okay. And if it has exceeded the elastic limit, then also it will come back, but there will be slight deformation. But what will happen in case of this fluid? Okay, what will happen in case of this fluid? In case of this fluid, even if you remove the shear force, do you expect that this fluid will come back to its original position? No, it will not come back, but it will keep on deforming, okay. So in case of solids, if I'm saying that the shear strain is theta, so if I'm saying that force, or say the shear stress force by area, which is denoted by tau, is directly proportional to theta, stress is directly proportional to strain. In case of fluid, stress is not directly proportional to strain. Okay. In case of fluid, stress is not directly proportional to strain. Rather, stress is proportional to the rate of strain or time rate of change of strain. Okay. So this is the basic difference between a solid and a fluid. And this d theta by dt, if you look carefully, is nothing but du by dy. How this is du by dy? Because this theta is the shear strain, which can be written as delta L by L. Where what is this delta L? This delta L is nothing but this deformation, okay, along on this plane, and say L is the length of this particular block, okay. So this delta L by L is theta. So instead of d theta by dt, if you put d dt of delta L by L, then this delta L is constant. It will come out of differentiation, and d dt of delta L, okay, d dt of delta L is what? This is some velocity. So basically du by dy, where y is nothing but L, because L is along the y direction, okay. Or you can use any convention. So this is the basic idea how Newton's law of viscosity came into picture. So your first unit, okay, your first unit, that is basic fluid properties. Apart from the fluid properties, this Newton's law of viscosity is very important. And there is a graph, if you have gone through the lecture, between stress versus rate of strain, which decides, depending upon the shape of the figure, you can know very carefully that whether it is a Newtonian fluid or a non-Newtonian fluid, or it is a Bingham plastic, okay. So this, or it is an ideal solid, or it is an ideal fluid. So just to recapitulate, the graph looks something like this. Tau, shear stress, du by dy. So a line passing through the origin of this graph, okay, sorry, yeah. So this is a Newtonian fluid. These are non-Newtonian fluids. Something like this is plastic, or something like this is, so this is an ideal plastic, this is a big ideal plastic, this is not an ideal plastic. If your graph, okay, if your graph or if your plot coincides with tau axis, and if your plot coincides with du by dy axis, then what happens? If it is coinciding with the tau axis, it means that du by dy equal to 0. So if du by dy is equal to 0, see, the value of tau is there, shear stress is there, tau is there, but for all this tau, what is the value of strain? The value of strain is the rate of strain is 0. So it is an ideal solid. And if your graph lies here, tau is every time 0, but du by dy value is there, then it is an ideal fluid. What is the definition of an ideal fluid? An ideal fluid is something whose viscosity is 0. So if viscosity is 0, then tau equal to mu du by dy. Okay, tau equal to mu du by dy. Or if you consider the most general form for shear stress, it is tau is equal to A plus B du by dy raised to the power of n. Okay. Now here this B is nothing but mu. Okay. This B is mu. If mu is equal to 0, okay. If mu is equal to 0, then tau is equal to A. This represents the plastic fluid. But if it is not a ideal plastic, or maybe not a plastic fluid, and if it is a Newtonian fluid, then we can write this as tau equal to mu du by dy. And if this mu is equal to 0, then whatever is the value of du by dy, whatever is the value of du by dy, tau is always 0. So this particular axis, x axis represents, or du by dy axis represent an ideal fluid, and this represents an ideal solid. Okay. So this is very important again. This is very important, this graph, because in competitive exams you might be given this graph, and one possibility is that they will label this as A, B, C and D, and in the options it will be given whether what is A, what is B, what is C, what is D. So this particular graph is very important. Okay. Now the next part of the question, what is the difference between fluid mechanics and hydraulics? Okay. So fluid mechanics is basically the study of fluids. Okay, the study of fluids, both fluids at rest as well as fluids in motion as a whole. A comprehensive coverage of the entire fluid flow phenomenon is fluid mechanics. But hydraulics, see, fluids consist of both gases as well as liquids. Okay, but in civil engineering, if you think carefully, uh, what are the most important topics or areas where fluid mechanics is important? It is the river flow, ocean engineering or coastal environments, then flow in porous media, that is groundwater hydrology, rainfall. Everywhere water is involved. So the various aspects associated with the flow of water, I mean the aspect of force, okay, force and the motion of water, so that is termed as hydraulic. However, in order to understand the motion of the fluid, it is no different from understanding the behavior of motion of water. It is no different from understanding the behavior of a fluid. Okay, only when you substitute the density and viscosity with the values for a water, you will be getting it as hydraulics. Otherwise everything is same. Okay, and one more important property is we consider that water is incompressible. So all the equations for incompressible fluid mechanics are valid for water. And when so hydraulics can be considered as a subset of fluid mechanics, where we deal with the water, flow of water. That is the only difference. So with this our introduction is over. Next we'll move to this week one's problem solving session. Okay, week one's problem solving session. Now I hope you have gone through the lectures of week one, and with this let us start with the problem solving part. So this is the first problem. You have to determine the mass density, specific volume and specific weight of a liquid whose specific gravity is 0.85. Okay, so you have to determine the mass density. What are the things that you need to determine? You have to determine the mass density, specific volume, specific weight, and the specific gravity is given to you. So please try this problem. I'm giving you a few minutes, and then we'll discuss the solution. We'll see. It is a very simple problem, and if you have gone through the lectures already, then this should not take much time. So please try from your side, and then we'll discuss the solution. Okay, here in the messages, Yash asked whether this lecture available later. Yeah, this lectures will be made available. This lectures will be made available to you. We'll upload this lecture in YouTube, and the YouTube links for this particular videos weekwise will be shared with you. So you don't have to worry about these lectures. Okay, welcome. Yeah, whatever answer you have obtained, if you have obtained, please in the chat box you can reply with your answers. Okay, fine. Density 850 kg per meter cube. And what about the other two? Specific weight 8.3 kilonewton per meter cube. And what about specific volume? Density is, yeah, specific volume is the inverse of density, yes. So it is 1 by 1, 1 by 850. Okay. So, okay. So in the problem, it is given that the specific gravity is equal to 0.85, and you are asked to calculate what is density, then what is weight density. Okay, say I'm writing this as gamma, and then what is the specific volume. say I'm writing the specific volume as V cross. Okay, so these three things you need to calculate: rho, gamma, and V, that is specific volume. Okay, now the you need to start with the only one value that is given to you, that is the specific gravity. So sorry. So what is specific gravity? Specific gravity, say I'm writing Sg, specific gravity is the ratio of the density of any matter that is under consideration divided by the density of water. Okay. Now here it is very important to remember one thing. Yash, not Yash, I think what, yeah, Dinesh obtained 850 kg per meter cube, which is fine. Okay, which is fine. But when he has obtained this value as 850 kg per meter cube, what is the assumption? The assumption is the density of water at standard temperature and pressure is 1000 kg per meter cube. Okay, so if nothing is given in the question, you can safely take this value as 1000 kg per meter cube, but you should always read the question very carefully. For this problem, since nothing was mentioned about the density of water, taking a value of 1000 kg per meter cube is okay. But sometimes in the questions, separately the density of water might be given that it is 998.2 kg per meter cube, or sometimes it may be given that you have the specific gravity with respect to, say, sea water is given. Okay, so something like that. So you should read the question very carefully. Blindly using the value of 1000 kg per meter cube. Okay, in most of the cases it will not cause any problem, but sometimes in some competitive exams they may intentionally provide you or supply you with the value of density of water which is different from 1000 kg, because our tendency is to generally use the value of 1000 kg. So just uh, in order to create confusion, they may supply a value. So whatever value is given in the question, you use that value. Otherwise you can use a value of 1000 kg per meter cube. Okay, so the specific gravity is rho by rho w is given as 0.85. So for this particular problem, since nothing is given to you, so you can safely assume the density of water to be 1000 kg per meter cube. Therefore rho will be equal to 0.85 into 1000, so which is rightly mentioned by Dinesh. It is 850 kg per meter cube. Now, what is this gamma or specific weight? Gamma, or the second part is, sorry, specific volume. Specific, the second part that has been asked is the specific volume. Now, specific volume V is 1 by rho, okay, 1 by rho. So, 1 by 850 unit will be meter cube per kg, okay. So, what is the value? Value is approximately 1.18 into 10 to the power minus 3. Okay, so the value is approximately 1.18 into 10 to the power minus 3 meter cube per kg. You can uh, you can recheck these values. Okay, you can recheck these values. There may, you can recheck these values. Okay, see, the intention of these live sessions is not to compute the correct answer. Basically the idea, okay, how to solve the problem, what should be the approach, that is more important. So 850 is fine. You can check the value of 1.18 into 10 to the power minus 3. I have done this, but you can still recheck. There might be some calculation error. Okay, in future also, for future reference also, I am telling you that there might be some calculation error. No need to assume that these values that I am writing here are always correct, but the approach is important. Okay, the approach is important. So we have obtained what we have obtained. We have obtained the value of density. We have obtained the value of specific volume. The last one that is remaining is the value of gamma. So what is gamma? Gamma is nothing but weight per unit volume. So see, I have used V for volume, okay, and for specific volume, what I have done for specific volume, I have used this, okay. So W by V. Now weight per unit volume, weight can be written as mass into acceleration due to gravity divided by volume. Mass by volume is what? Density. So basically rho g is this specific weight. So if rho g is specific weight, so gamma equal to rho g is the specific weight. The value of rho is 850 kg per meter cube into g is 9.81. Okay. So since everything is in SI, so it will be Newton per meter cube. Okay. Now 850 into 9.81 is around 8338.5 Newton per meter cube, or if you express it in terms of kilonewton, it will be approximately 8.34 kilonewton per meter cube. Okay, so you can recheck the calculations, no problem, but the idea is this. Okay, now as Dinesh has already mentioned the answer, density is 850, fine. Specific weight 8.3 kilonewton per meter cube, fine. Density is inverse. Yeah, here I would like to mention one more thing. See, uh, similarly to the case of density of water, the value of G. Okay, uh, if you sit for competitive exams, definitely they will supply with the value of G. Okay, so whatever value of G is supplied to you, you use that value. Okay, if a value of 9.81 is given, you use meter per second square is given, you use that value. Or if a value of 10 meter square per second square, you use that value. So please, before solving the problem, especially for competitive exams, please look at the values that has been supplied to you. You look at the units carefully. Okay, you look at what are the values, or rather I'll focus on this, that whenever you read a question on a rough page, you make a list of what are the variables, the values of the variables that are given to you. Say variable v1, v2, v3, whatever is given to you, make a list. Okay, so that will avoid some unnecessary errors. Okay, so you please do that. So I hope this problem is clear. It was a very simple problem. Okay, is this problem clear? Okay, so since there is no doubt, I am assuming that the problem is clear. Now let's move to the second problem. For the second problem, so this is the problem. Okay, a flat thin plate is dragged at a constant velocity of 4 meter per second on the top of a 5 millimeter deep liquid layer of viscosity 20 centipoise. If the area of the plate is 1 meter square, find the drag force. Okay. Assume the variation of velocity in the liquid to be linear. The answer is already supplied here, 16 Newton. As I told you, the final answer is not important. The approach or how we have solved the problem, that is of utmost importance here. So, please take some time and try to solve this problem. Then we will discuss it. Okay. And wherever possible, please draw a rough problem sketch. Try to visualize the problem and then you go for solving. Okay, look at the data carefully. What are the unit? See here, viscosity of 20 centipoise is given. So how will you use that viscosity? What exactly is that viscosity? Whether it is uh, dynamic viscosity or kinematic viscosity, everything you need to decide. Okay, looking at the unit. So look at the question carefully and then we'll try to solve the problem. Okay, you take some time, you try to solve it from your side and then we'll discuss. Sorry. Yeah. I have highlighted the important things, the important parameters where you need to focus on for solving this problem. Okay, you got the answer. Fine. 1 poise is equal to 100 centipoise. See, yeah, that is fine. Uh, Whenever you solve the problem, hopefully you have also done the same. If it has been not specifically asked in the question that you need to report the answers in a certain unit system, it is always advisable to use the SI system of units. Okay, SI units, and got the answers by using Newton. Yeah, yeah, yeah. You have to definitely use Newton's law of viscosity. And if you have got the answer, very good. Please wait for some more responses. Let's see if somebody else gives some response. Otherwise, we'll discuss the solution. Okay. What about Surmita and Yajani? Okay. So let us discuss the problem. Sorry. Okay. So in the question, what is given to you, that a flat thin plate is dragged at a constant velocity on the top of a 5 mm deep liquid layer. Okay. So this is the scenario. Okay. So there is a 5 mm deep liquid layer. Okay. So if I draw a simplified figure, this is the liquid layer. Okay. This is the liquid layer. Okay. Now the variation of the velocity in the liquid is linear. It is given in the question that the variation in the velocity is linear, means along the depth the variation is linear. Now why I have drawn it like this? Because on the top there is a plate, okay, which is being dragged. Okay, so if this is being dragged from no slip condition, the relative velocity of the fluid particles on the top will be equal to the relative velocity between the fluid particles in contact with this plate should be zero. So for that, the velocity of the fluid particles on the top of the layer should be equal to the velocity of the plate with which it is being dragged. So what is the velocity? The velocity is 4 meter per second. So here this is 4 meter per second. Okay, and this depth is 5 millimeter. 5 millimeter. Okay. Now, is this the problem figure that you have visualized, Dinesh? Is this the same problem figure? Yeah, good. Fine. Now, what else is given to you? It is given to you that the area of the plate, that is, see, we are only looking at the side view. If you look from the top, then the plate will have some area. Okay, the plate will have some area, and if you look from the top, and the area of this plate is 1 meter square. Okay, and apart from that, the viscosity of 20 centipoise. Now centipoise, what type of viscosity is this? Is it dynamic viscosity or is it kinematic viscosity? What type of viscosity is this? Dynamic or kinematic? Dynamic. Good. So this is the unit of dynamic viscosity. See, the unit of dynamic viscosity in SI unit is, it is Newton second per meter square, and if you convert this into CGS, okay, in short we write that as poise. Now in the question it is given as 20 centipoise, if I am not wrong. Yeah, 20 centipoise. So what is the relationship between poise and this Newton second per meter square? 1 poise is equal to how much Newton second per meter square? 1 poise equal to how much Newton second per meter square? Dinesh, how much you have used? 100. Poise and Stokes. Sorry, poise and relation between poise and Newton second per meter square. Is it really 100? I don't know, sir. Okay, Dinesh, fine. You don't know, that is a different part. But for the problem that you said you have obtained the answer, how much value you used? Did you use? Did you use one poise is equal to 100 Newton second per meter square? Is this what you have used? Okay. Then I don't know how you obtained the. Yes, yes, yes. Somebody Yajni replied 1 by 10 Newton second. Yes, point 1. That is the correct answer. Yes, good. So 1 poise is equal to 0.1 or 1 by 10 Newton second per meter square. So in our case, it is how much? It is given to you that it is 20 centipoise. So 20 into 10 to the power minus 2. Okay, 20 centipoise, 20 into 10 to the power minus 2 into 0.1. Okay, so this is the value of mu. Now tau is equal to mu du by dy. Now if tau is equal to mu du by dy, the value, see, you need to obtain the value of tau, or not tau exactly, force. So for force you need stress, so tau, value of mu is given. What remains is the value of du by dy. Okay, so what is the value of du by dy? The value of du by dy, see on the top, du by dy is what? It is the velocity gradient. So say u is equal to, since it is a straight line, a y plus b. Okay, this is the equation of a straight line, a y plus b. U at y equal to c 5 mm. So 5 mm is 5 into 10 to the power minus 3 meter. So at this value of y, what is the value of u? It is 4 meter per second. And what is the value of u at 0? It is 0, means here. Okay. So there are two unknowns, a and b. There are two equations. One for the value of u at y equal to 5 mm and one for the value of u at y equal to 0. So if you use these two conditions here, you will be getting the value of a and b. Okay, you'll be getting the value of a and b. So what are these values? Let's see. Okay. Hmm. So u is equal to a y plus b. Okay. Now the value of u is 4 meter per second at uh, y is equal to how much? 5 into 10 to the power minus 3 plus b, and u is equal to 0 at y equal to 0. So this will be u is equal to 0 at y equal to 0. So when you put y equal to 0, b will be equal to 0. And what is the value of a? Value of a is equal to 4 divided by 5 into 10 to the power minus 3, or I can write this as 10 to the power 3. Sorry. Yeah. Let us not skip this thing. 5 into 10 to the power minus 3. Okay. So this thing can be written as, if I multiply a 10 to the power 3 here, then I have to multiply a 10 to the power 3 in denominator as well. So this becomes 1. So finally we're left with 4 into 10 to the power 3 divided by 5. This is the value of a. So how much this is? 800. So this value is 800. So what is the variation? U is equal to 800 times of y, where y is in meter and u is in meter per second. Okay. So what will be del u by del y? Del u by del y will be 800. And what will be tau? What will be tau? Tau is equal to mu del u by del y or du by dy. So the value of mu is 20 into 10 to the power minus 2 into 0.1 into 800. So how much is the value? 20 into 10 to the power minus 2 into 0.1 into 800. So the answer comes out to be 16 Newton per meter square. But this is not all. Why this is not all? Because in the question it is given that you have to find the drag force, but this is only stress. Okay, so shear stress is equal to the force with which the plate is dragged divided by the area of the plate. In the question it is given that the area of the plate is 1 meter square. So that's why the drag force is F is equal to tau into A. The value of tau is 16. The value of A is 1 meter square. So finally this gives you 16 Newton. Now is it clear, this problem? Now Dinesh, I don't know how come by using a factor of 100, maybe you got the answer. Okay, that is fine. But if you have used the conversion factor is 100, then it is not correct. Okay, so the correct conversion is 1 poise is equal to 0.1 Newton second per meter square, and if it is kinematic viscosity, then the CGS unit is Stokes, and 1 Stokes is equal to 10 to the power how much? 10 to the power minus, anyone? 10 to the power minus 4 meter square per second. Okay, now is the problem clear? Okay, you did as it is, but why you wrote 100, Dinesh? Means when I asked about that conversion factor, you wrote 100, no? Or maybe that was by mistake, you wrote 100. Anyways, uh, it is fine. Okay. I got it. So you thought that I asked about poise and centipoise. No. I was asking about poise to Newton second per meter square. Yeah. Okay, fine. Then it is fine. So again, this is a very important stress point. This conversion factor should be very much clear to you. Okay. And then I'm fine. Okay, then it is fine, Dinesh, that You have done the same thing. There was a miscommunication. Okay, fine. Thank you. Now let's move to the next problem. So this is the next problem. You have to find the depth of a point below water surface in sea. Okay, you have to find the depth of a point below water surface in sea where the pressure intensity is 100.55 kilonewton per meter square. The specific gravity of sea water is 1.025. Okay, means you have to determine the location of a point which lies below the free surface of ocean or sea where the pressure intensity is 100.55 kilonewton per meter square and the specific gravity of seawater is given to you, which is 1.025. Please try this problem. Okay, please try this problem. It is again a very simple problem, but there are few delicate details associated with this. Okay, which you'll see. But you first of all try this problem and tell me the answer that you have obtained, and then we'll look into the solution. So this particular problem uh, involves the hydrostatic pressure distribution. Hydrostatic pressure distribution. So that is the first hint. It's a very simple problem, but yeah, first of all, you please tell me the answer that you have obtained, and then I will tell you about the critical points that you need to keep in your mind. 9.9 meter. Okay. So Dinesh, this depth that you have obtained, 9.9 meter, is it from absolute? Is it from the measure of absolute pressure measurement or gauge pressure measurement? Yeah, sure. Okay, so you have used the gauge pressure. Fine. Can you solve the same problem uh, from the absolute pressure measurement? consideration? Dinesh, please find and tell me what is the answer. Sorry. By gauge pressure 5.4, by absolute pressure 9.9. Okay. So I think in absolute pressure, this calculation you have considered that this pressure intensity of 100.55 kilonewton per meter square is the absolute pressure, and in gauge pressure calculation you might have considered that this pressure 100.55 kilonewton per meter square is the gauge pressure, right? Yeah, fine. I'll come to that. But let us solve this problem from both the considerations. Okay. Okay. So in the question, it has been given that, yeah, say this is the free surface of the sea and you have to find the depth, okay, to a point P where the pressure intensity is given by 100.55 100.55 kilonewton or 10 to the power 3 newton per meter square or pascal is the pressure. Okay. Now nothing has been clearly mentioned in the problem that whether it is in terms of absolute scale or in terms of gauge scale. Okay, you don't have to worry about your exams or maybe competitive exam because there it will be specifically mentioned. Okay, but since here it is not mentioned, I intentionally selected this problem just to make you guys realize the importance of these two terms. See, mm, if you remember, what is the difference between gauge pressure and absolute pressure? If say this is the pressure scale, okay, and this line represents absolute zero and this line represents the atmospheric pressure, Now, whenever say you have to determine the pressure at any point P here, sorry, any point B, suppose here. If you are measuring this pressure with respect to absolute zero, that is from vacuum, okay, then this pressure is known as the absolute pressure. I am very much sure that you, sorry, absolute pressure, you know all these things, but just for clarity and recapitulate, okay, recapitulation purpose, I am repeating this. Now, if you are measuring this pressure with respect to this, that is the atmospheric pressure, then we call this gauge pressure. Okay. Similarly, if suppose you want to find the pressure at a point here, means where the pressure is below atmospheric, then same if you are measuring with respect to the absolute zero, it is atmospheric, sorry, absolute pressure. And if you are measuring with respect to atmosphere, okay, then it is known as vacuum pressure. Okay, why vacuum pressure? Because it is vacuum with respect to the atmosphere. The value of the pressure here is, the value of the pressure here at point B is less than atmospheric pressure, so that's why it is known as vacuum pressure. Okay, in terms of the gauge pressure scale it is vacuum pressure, and in terms of absolute zero it is always absolute pressure. Now you have to find the pressure at some point P which lies below the C, okay, and the pressure intensity is given to you. In the question nothing has been mentioned, as I told you. You don't have to worry for actual exams, means where the questions, in the questions it will be clearly mentioned whether it is in absolute scale or in gauge scale. Okay, and one more thing, majority of the cases the standard is to report everything in gauge scale. Okay, so first of all let us see in gauge scale. Okay, let us see the calculation in gauge scale. Okay, okay, fine. So in gauge scale we know that the hydrostatic pressure distribution is P is equal to rho G H. Okay, the value of pressure is given to you which is 100.55 into 10 to the power 3 Newton per meter square. Rho. Now rho is not directly given, it is given that the specific gravity of seawater is 1.025. So if the specific gravity of seawater is 1.025, then the density of seawater will be 1.025, which is the specific gravity, multiplied by 1000. Okay, so this gives us the density rho, where 1000 is the density of the water. As I told you, if nothing is mentioned, you can safely assume the density of water to be 1000 kg per meter cube. Into G is, let us take 9.81, into H is this height H. Okay, this height H. So from this, what will be the value of H? The value of H will be 100.55 into 10 to the power 3 divided by 1.025 into 1000 into 9.81 equal to how much? Let's see. 100.55 into 10 to the power 3 divided by 1.025 into 1000 into 9.81. So this is 9.99 meter approximately. Okay, so this is from the gauge pressure point of view. Now if you consider the atmospheric pressure consideration, okay, now if you consider the atmospheric pressure consideration, sorry, I'm not clearing the canvas because the figures are already here. So I'm just deleting the calculations with respect to the gauge pressure. Okay. Now, yeah, with respect to gauge pressure calculations, okay, gauge pressure calculations, yeah, let us take this one. See, on the top of the free surface, it is atmospheric pressure, PA, okay. So at this point P, it will be atmospheric pressure plus the pressure intensity that is given to you. So that will be the absolute pressure. What is absolute pressure? Pressure in excess of the atmospheric. So atmospheric pressure is there plus the pressure because of this fluid lying above this point P. Okay. So 100.55 into 10 to the power 3 is the pressure at the point. Let us say we don't know whether this pressure is absolute pressure or gauge pressure. We can check this. Okay, how we can check means it is not a direct check. What is the value of atmospheric pressure? What is the value of approximate atmospheric pressure? What is the value of atmospheric pressure? Standard atmospheric pressure? Anyone? Dinesh, what value you have used? You have obtained a value now for atmospheric pressure. So, uh, okay, am I audible? Yajni, am I audible? Okay, so I think the network issue is from Dinesh's end. Anyways, let's see. The value of atmospheric pressure is 101,325 Newton per meter square. Okay, and here it is. Yeah. Now, out of these two, out of these two, the pressure intensity that is given at that point and atmospheric pressure, which pressure is higher? The value of 101,325 is higher or value of this one is higher? Which value is higher? Which condition is correct? Whether P that is given to you, is it greater than atmospheric pressure or P is less than atmospheric pressure? You just find the difference and calculate. So if you find this value P minus P atmospheric, then it will be 100.55 into 10 to the power 3 minus 101,325, which is coming out to be minus of 775. So if this is minus, it means that atmospheric pressure is greater than P. Okay, so this condition is correct. Okay, so if this condition is correct, then what happens? If this condition is correct, it means that on a diagram like this, if this is the atmospheric pressure, okay, point atmospheric pressure is greater than P, it means that point P lies here. Okay, but is it possible physically? Because it has been already mentioned in the question. It has been already mentioned in the question. See, there are two scenarios possible. The pressure at point P is less than P atmospheric. It means that one possible explanation is it is only actually the gauge pressure measurement, means whatever is given to you, it is, if this is absolute pressure, it means that the point P lies below the atmospheric pressure line, which is not possible. Why this is not possible? Because physically this point lies beneath the free surface of the sea. So definitely the pressure is high, means if you think logically, physically the pressure is higher than the atmospheric pressure, but the calculations are telling you otherwise. So the only reasonable explanation is that this pressure intensity P that is given to you is in gauge scale. Okay, so there is no need to use the atmospheric scale. And if you want to use the absolute scale, then what you need to do is, with this you add atmospheric pressure, so that will give you the value of absolute pressure at point P. Okay, so the answer is 9.9. Is it clear? Is it clear? Okay, fine. So you need to be very much careful. Okay, you need to be very much careful. So let's come to the next problem, which is the last problem for today's session. A figure is shown here. Okay, a figure is shown here where there is a circular plate submerged vertically inside water. This is the free water surface. The center of the circle lies 2.5 meter below the free surface of the water, and the diameter of the circle is 1.2 meter. Okay, you have to determine the total pressure and the position of the center of pressure. So this is basically from the chapter hydrostatic forces on surfaces. It's a very simple problem. You have to directly use the formula, nothing else. So please find the answer and tell me what is the answer. So this is the case. Okay, let's see the solution because not much time is left. So the area of the plate is given. Okay, the area of the plate is pi d square by 4. As given in the question, the diameter of the plate is 1.2 meter. So the area is 1.13 meter square. Now it is given in the question that the center of the circle, okay, lies 2.5 meter below the free surface and the plate is vertically submerged. Okay, for a circular plate, the center of gravity and the center of the circle of the geometrical shape coincides. So the position of the position of the CG below the free surface, that is x shown by x dash, is 2.5 meter. Okay. So what is the expression for total pressure force? What is the expression for total pressure force? The expression for total pressure force, F is equal to rho g a x dash. In the question it is given that the fluid is water, so the value of rho is 1000 kg per meter cube. The value of g is 9.81 meter per second square. The area of the circle is pi d square by 4, where the value of d is 1.2 meter and the value of x dash, as we have seen, is given in the question, which is 2.5 meter. So everything that you need for computing the total pressure force is given to you. Okay. So the value is how much? Rho is 1000 into 9.81 into area is pi into 1.2 square by 4 into 2.5. So let's calculate. It is 1000 into 9.81 into pi into 1.2 square into 2.5 divided by 4. So the answer is approximately 27.7 kilonewton, and if you want precise answer, then it is 27,737.12 Newton. So approximately 27.7 kilonewton. So this was about the first part of the problem, total pressure force. What about in the second part? You have been asked to calculate the distance of this point C from the free surface. So for that, what is the formula? It is denoted by H dash is equal to Ig Ax dash plus X dash, where A is the area of the plate, X dash we have already seen is the location of the centroid from the free surface, Ig is the moment of inertia, the second moment of inertia. Okay. So for a circle, what is the value of Ig? The value of Ig for a circle is pi d4 by 64. Okay, or here we have used small d, so it is pi d4 by 64. Okay, so pi d4 by 64, you can calculate this. Now once you have calculated the value of pi d4 by 64, you can, which is approximately 0.1018. Okay, you can find the value of h dash, which is 2.536 meters. So this is the answer. Now this was a very simple problem, but here I would like to suggest something. You don't have to memorize the equations. For competitive exams, you do not have sufficient time to derive these expressions. Okay, so definitely you need to remember something. So you remember the general case, that is when a general plate is immersed in an inclined position. Okay, you remember the general case, which will involve some value of theta. You take the value of theta equal to 0 degree for horizontal case, theta equal to 90 degree for the vertical case, and then theta equal to any other value for the inclined case. Okay, you remember that expression? Apart from that, in any standard textbook of fluid mechanics or hydraulics, you will find that there is a table. Okay, a table which for different geometrical shapes, for example a rectangle, a triangle, a circle, a trapezoid, will give you the position of the centroid, okay, the position of the centroid, and the moment of inertia. Okay, so you please remember those values, and you at the same time you also remember about which axis is that moment of inertia. Is it about the centroidal axis, or is it about the base, or is it about the vertex? Okay, so about which axis it has been calculated or the expression is given, you try to remember that. Okay, that will save you a lot of time during exams, and this particular chapter is very important for competitive exams. Okay, so that's why you try to remember this table. You take the example of any standard text on fluid mechanics. Okay, so that's it for today's session. uh, do you have any doubt to ask? If you have, you can please ask, or otherwise we'll stop. Any doubts? Okay, so if there is no doubt, then thank you very much. We'll meet again at 4 p.m. on next Saturday. uh, Thank you. So you can please leave the meeting. Thank you.